Okay, hi folks, this is the second part of our inductors lessons, and we're really talking about inductors in AC circuits. And just like capacitors that have capacitive reactance or resistance to AC signals, then inductors also have reactance. They are active components, and their reactance or resistance, if you like, is dependent on the frequency of the AC signal. So the inductor is another frequency dependent component. When you place it in an AC circuit, the inductor has an inductive reactance that depends on the size of the inductor, or should I say the inductance of the inductor, which is measured in henries, and the frequency of the AC supply, which is measured in hertz. Now, because inductors operate on a principle of a changing magnetic field induces a back EMF, and the rate of change of current is directly proportional to the EMF that's produced. If you have a higher rate of change of current, in other words, if you have a higher frequency, then you will have a bigger EMF and hence a bigger resistance to that or opposition to that AC current. So the reactance is directly proportional to the frequency. The bigger the frequency, the bigger the reactance. And similarly, the bigger the inductor, the higher the reactance. So XL, the reactance of the inductor, is equal to 2 pi FL. It's similar to resistance in DC circuits, but it's frequency dependent. And reactance is measured in ohms. And because reactance is measured in ohms, we can use Ohm's law as long as we use the RMS values of the voltage and the current. So XL, the reactance of the inductor, equals VRMS over IRMS. And as usual, a little example will make things hopefully a wee bit clearer. If we've got an inductor here, and it's a 0.3 Henry inductor, and it's connected to an AC supply that has got an RMS voltage of 120 volts and a frequency of 60 hertz. Calculate the inductive reactance of the inductor in this circuit. And calculate the effective current, that's IRMS, in the circuit when the supply voltage is 120 volts RMS and the frequency is 60 hertz. And if the frequency of the supply is increased to 400 hertz, state what happens to the reactance of the inductor and the current in the circuit. Well, for part A, the inductive reactance XL will be equal to 2 pi F times L, so 2 pi times 60 times 0.3 gives us an answer of 113 ohms. For part B, if we want to work out the current, this is Ohm's law. I equals V over R. 120 over 113 gives us 1.1 amps. Now in this case, if the frequency is increased, the reactance is going to increase because XL equals 2 pi FL. So if F goes up, XL goes up. The reactance goes up. And if the reactance goes up, see part 2, what happens to the current in the circuit? The current will decrease. So this is the opposite of capacitors. Capacitors like high frequencies. Capacitors will let high frequencies pass. Inductors don't like high frequencies. Because the higher the frequency, the higher the rate of change of current. So the higher the back EMF and the greater opposition there is to high frequency AC signals. Inductors like low frequencies. Right, I thought I would do a wee demo then to compare capacitors and inductors with a variable frequency supply, and at the same time we're going to determine the reactance of each and the capacitance of the capacitor and the inductance of the inductor. Here we go then. Okay folks, got a wee demo today to investigate the relationship between the frequency of an AC supply and the current in various components. We're going to look at a resistor, we're going to look at a capacitor, and we're going to look at an inductor and see how the frequency of the supply affects the AC current in the circuit. So firstly, I have a resistor, a variable resistor, which I've just set at some random value. I'm going to change the frequency on this signal generator. Now the signal generator is set at 500 hertz. There's a little adjuster that matches up with that little black mark at the top there. So that's 5 times 100, 500 hertz. And that 500 hertz AC is supplying a current to this circuit, and we're getting a current of about just over 6. I'm using the top scale there, so that's milliamps. So 6 milliamps. And I'm going to change the frequency of the supply. That's the amplitude. So that's the loudness of the signal, which is the voltage, the RMS voltage, if you like. So I'm not going to change that. In fact, I'm going to adjust that so that it's 6. Okay. And then I'm not touching that. I'm not touching the amplitude. We're only going to change the frequency. Watch what happens when I change the frequency of an AC supply with a resistor in the circuit. Here we go. Frequency going up. You can hear it. And you can see there's no change. We can go down the way. You can hear it. And there's no change. I'm down at 200 hertz. Right? That's about 200 hertz. Back up to 500. And no change on the ammeter. So, no change in a resistor circuit when you change the frequency of the AC supply. Let's change the resistor for a capacitor. Right, I've placed a capacitor in the circuit instead of the resistor. Capacitor's connected to the AC supply. It's set at 500 hertz, and we're getting a current on the ammeter of about nearly 3.4 milliamps. And I'm going to change the frequency. You'll be able to hear it. Hopefully you'll be able to see it. This is a capacitive circuit. Increase the frequency. And as the frequency goes up, the current goes up. As the frequency goes down, the current goes down. And in fact, when you double the frequency, you double the current. Let's do this just now. That's 250 hertz. It's about 250 hertz. And we're getting 2 milliamps. Let's go up to 500 hertz. That's 500 hertz. And we're getting 4 milliamps. So double the frequency, double the current. Right, let's go back down again. Alright, I have replaced my resistor with a capacitor, an unknown capacitor there, and we are going to use an AC supply of 400 hertz here. So adjust that to 400. So 400 hertz. And we're going to measure the current in the circuit, but we're also going to measure the voltage across the capacitor. These are RMS voltages, AC effective voltages. And from the RMS voltage and the RMS current, we should be able to work out the reactance of the capacitor. Remember, reactance is like resistance that capacitors have in AC circuits, but that reactance depends on the frequency. So, here's what we're going to do. We're going to measure capacitive reactance, set the signal generator to 400 hertz, measure the voltage across the capacitor and the current in the circuit, and then using Ohm's law, XC is the reactance of the capacitor, will be the RMS voltage divided by the RMS current. Here we go then. Here's the RMS voltage. It's about 0.8 volts. So 0.8 volts. Let's put that in there. And the current is about 2.5. using the top scale because we're in milliamps. Each wee division is 0.2, so that's 2.5 milliamps. 2.5 milliamps in there, so that'd be 2.5 times 10 to the minus 3. And then we can work out our capacitive reactance. And once we've got the reactance, we can calculate the capacitance of the capacitor using the relationship we've already got, rearrange it for C, and then we can calculate it once we've got our reactance. Let's turn that noise off and get the reactance first. Because the reactance, remember, is just the RMS voltage, 0.8, divided by the RMS current, 2.5 times 10 to the minus 3, is 320 ohms. Remember, that's at 400 hertz. If we change the frequency of the supply, at higher frequencies we'll get more current, so we'll get less reactance. That's for another day. But anyway, let's use that reactance now and put it into this equation. 320 ohms. Remember, the capacitance of the capacitor will be 1 over 2 pi f xc. We've just calculated xc. So my 320 can go in there. I do that on my calculator. I'm going to get 1 divided by 2 times pi times the frequency was 400 hertz times the reactance, we've got 320, gives us 1.24 times 10 to the minus 6 farads. So rounding that should be about 1 microfarad. And let's have a look at our capacitor. Let's take off that wee bit of paper. It's a 1 microfarad capacitor. There you go. That's measuring reactance and measuring capacitance of a capacitor using an AC supply. So that was the setup for the capacitor. Signal generator set at 400 hertz. We worked out a capacitive reactance of 320 ohms. And from that 320 ohms and the frequency of the supply, we could work out the capacitance of the capacitor, which was 1 times 10 to the minus 6 farads, 1 microfarad. Going to have a little look at an inductor next. Okay, it's the turn of the inductor this time. I've put a little inductor. It's actually a transformer coil that I found. Can I put that noise off just now? I just found a wee transformer coil in the cupboard, and if you look, it's got 120. Let me see. It's got 120 turns plus 120. It's a 240 turn coil. I've put a little core through it, and that can act as our inductor. I've no idea what its inductance is, but maybe we could measure it later on. We're going to do the same as before. We're going to connect it to a signal generator and measure the current that's flowing. I'm going to vary the frequency and see what effect that has on the current in the circuit. So let's turn that on. I'm going to use 4000 hertz this time. Quite a high frequency. So 4000 hertz. There's the current at the moment. Just about 5 milliamps. Watch what happens when we change the frequency. I'm going to put the frequency down. Remember, with capacitors, there's a direct relationship. If you increase the frequency, you increase the current. Watch what happens this time. Let's increase the frequency. I'm increasing the frequency and the current's going down. If I decrease the frequency, the current's going up. So inductors behave in the opposite way to capacitors. At higher frequencies, you get less current, an inverse relationship between the frequency and the current. Inductors like low frequencies. Lower frequencies, higher currents. Higher frequencies, lower currents. And again, we can make some measurements of frequency and current and measure the inductive reactance of our inductor there. Let's do that. Set it at 4000 hertz, and we're going to make a note of that current And we're also going to measure the RMS voltage across our inductor there. Right, there's the plan. We're going to measure the inductive reactance of the inductor and hopefully its inductance by setting our signal generator firstly to 4000 Hertz. Measure the RMS voltage across the coil, measuring the current in the coil, working out the reactance using Ohm's law, VRMS over IRMS, and then using that reactance we can work out the inductance of the inductor, rearrange that relationship for L, and hopefully that'll be us. So, signal generator at 4000 Hertz. There it is, it's set at 4000 Hertz. I have got my little coil here. Remember, it's a little 120, 240 turns on it. Just found it in the store, got a wee iron core in it, so I've put that on the symbol. And we're going to measure the RMS voltage. And we're up to 10 volts here. That was the only shunt I could find, so it's about 0.4 volts. 0.4 volts. Let's add that on. And the current is about 5.2 milliamps. 5.2 milliamps. Let's turn that off. Okay. 5.2 times 10 to the minus 3. Okay. Our inductive reactance then is the RMS voltage, 0.4, divided by 5.2 milliamps is 77 ohms. Now remember, that's only at that frequency. If we change that frequency, remember, if we increase that frequency, it's going to decrease the current. So an inductor, by increasing the frequency, you're increasing the reactance because the current goes down. Opposite's true as well. If you decrease the frequency, you get more current, so there must be less reactance. So reactance is a frequency dependent quantity, and we are doing it at 4000 Hertz. So this is only for 4000 Hertz. The reactance of that inductor is 77 ohms. Let's turn it off. So if that's 77 ohms, then we can work out what the inductance of our inductor is by substituting in the 77 ohms for the reactance. Again on our calculator, 77 divided by 2 times pi times 4000 is 3 times 10 to the minus 3, or 3 millihenries. So 3 times 10 to the minus 3. Now I have no idea what that coil is, 240 turns with a iron core in it. I could try and find out. We'll have a go at that, but there you go. That's working out reactance, which is dependent on the frequency, and then working out the inductance based on that reactance and based on that frequency. Right, I did a wee Google search and I found Wheeler's formula for working out the inductance of a coil. So there it's there, L equals N squared mu A over L. Now we know what all those quantities are, or we can look them up. N's the number of turns on the coil. Mu is the permeability of the core material. Now we can look that up. A is the area of the coil and L is the length of the coil. So the area, I measured it, it was 7 centimetres by 5 centimetres and it was 2 centimetres long. I then went and I looked up the engineering toolbox for the relative permeability of iron, and it's 0.25. So if we want the permeability of the core, it will be 0.25 times the permeability of free space. Now, the permeability of free space is on your data sheet. It's 4 pi times 10 to the minus 7. So if we multiply that by 0.25, we'll get mu that we can put in this relationship. So let's calculate that. So there's our relationship. L equals N squared mu A over L. N was 240. Mu is going to be 0.25 times 4 pi times 10 to the minus 7. And the area of our coil, well, it was 7 centimetres by 5 centimetres. Let's move that out of the road. So 7 centimetres by 5 centimetres. And we want to divide all of that by the length of the coil. Well, the coil was only 2 centimetres thick. If I do all that on my calculator, I get an answer for the inductance of the coil of 3.17 times 10 to the minus 3 henries. But my lengths are all to 1 sig fig, so if we round that to 1 sig fig, it's 3 millihenries. So that was just a wee bit of Googling and research to see if we were in the same ballpark with the result that we got in the demo. And there's our demo result once again, and we got 3 millihenries. There you go then. Okie dokie. See you in the next one. Let's look at applications then of capacitors and inductors. Well, they're reactive components, and they are used in audio systems as filters to ensure that the correct audio frequencies are sent to the correct loudspeakers. Very expensive loudspeaker systems, they will have a section in it called the crossover network. And what the crossover network does is it makes sure that each frequency goes to the right loudspeaker. So if capacitors have got low reactance to high frequencies, and inductors have got low reactance to low frequencies, then a capacitor is used in series with the loudspeaker that produces the high frequencies. It's usually called the tweeter. So a capacitor is used in series with a tweeter because you want your high frequencies to come out that small upper tweeter speaker. It's the speaker that produces the high frequencies. And an inductor is used in series with the woofer that produces the low bass frequencies, so that it will block the high frequencies but allow the low frequency signals to pass to your woofer. A defibrillator is another example of where a capacitor is used and an inductor is used to ensure the correct operation of the device. A defibrillator, or to give it its full name, an AED, an automatic external defibrillator, is used to restart the normal beating of a person's heart. And the way that this works is it's usually a portable battery operated device. There should be one in every school, there should be one in most public areas, and they should be able to be used by all members of the public. So if someone has what appears to be a heart attack or cardiac arrest, then they should be able to use this device to help restart the normal beating of a person's heart. So here's how it works. A battery along with a transformer is used to increase a DC power supply to around about 5,000 volts. That 5,000 volts is used to charge up a capacitor when the switch is moved to position 1. And then once the capacitor is charged, there's usually an indication from the machine that you have to stand clear. And when you stand clear and you move the switch to position 2, when the switch is pressed, the capacitor discharges through the patient. Now, if there was only a capacitor there, it would discharge instantly through the patient. But what you do have to do is you have to allow enough time for the charge to pass through the patient's heart so that it can start the normal beating of their heart again. So an inductor is used to oppose the change of the current, and that ensures that the current is delivered to the patient at a high enough level for the required time. And an inductor is used instead of a resistor, because if a resistor was used, then heat would be produced in the resistor. But an inductor makes sure that all the energy that's stored in the magnetic field around the inductor then gets passed on to the patient and isn't wasted as heat in a resistor. Here's an example from the 2017 paper. A capacitor and an inductor are used in a hi-fi loudspeaker circuit. There's a capacitor in series with the tweeter and an inductor in series with the woofer. Explain why a capacitor is used in series with the tweeter. Explain why the inductor is used in series with the woofer. And when the frequency of the input signal is 3 kHz, the capacitor and inductor both have a reactance of 8 ohms, and we have to calculate the capacitance of the capacitor and the inductance of the inductor. So part A, it allows high frequencies to pass to the tweeter and blocks low frequencies. Part B, your inductor is used with a woofer to allow low frequencies to pass to the woofer and blocks high frequencies. In part C, you would use your capacitive reactance relationship, XC equals 1 over 2 pi FC, and rearrange it to find C, the capacitance of the capacitor. You'll get 6.6 microfarads, or 6.6 times 10 to the minus 6 farads. And same with C part 2, the inductance of the inductor. You would use XL equals 2 pi FL, rearrange it to work out L. So L would be XL over 2 pi F, and that would give you 0.42 millihenries. Inductance questions always seem to be at the end of the paper, and after 2.5 or 3 hours you probably get quite tired by the time you get to these, but there's very little they can ask. Tends to be the same sort of question every year, calculating reactance or describing and explaining the use of capacitors and inductors in various electrical circuits. That's it. See you in the next one.